Today, we are diving deep into the electric vehicle battery lifecycle. We're going to uncover exactly why localized, closed-loop recycling isn't just a nice environmental talking point. It's actually a massive financial opportunity. We'll be looking at this from a lifecycle standpoint, an industrial feasibility angle, and crucially, an investor's perspective. You know, the shift to electric vehicles is accelerating globally. But what happens when those millions of huge battery packs finally reach the end of their life? Well, answering that single question is spawning an entirely new industrial sector.
Here's our roadmap for today. We'll start by tackling the macro supply chain bottlenecks. Then we'll dive straight into the pros and cons of the actual recycling technologies and wrap up with a look at the future of the circular economy. Let's get right into it.
All right, part one, the EV supply chain bottleneck.
To really grasp the urgency here, you've got to see this number, 21 million. That is the estimated number of cumulative end-of-life battery packs we are going to generate between 2015 and 2040. Just let that sink in for a second. 21 million massive, highly complex battery packs. It's not some distant future environmental issue. It's an immediate supply chain reality. As EV sales hit their projected rapid growth over the next decade, this tidal wave of spent batteries is going to hit the market. If we don't have the infrastructure ready, we're looking at a devastating bottleneck. But if we do, well, it represents an incredible secondary mine for critical materials.
Now take a look at how geographic vulnerability plays into this global production. We've got 59% of the world's cobalt coming straight out of the Democratic Republic of Congo and 44% of its lithium coming from Australia. If you're an investor, or honestly anyone concerned with long-term industrial sustainability, that uneven material distribution is a glaring red flag. It heavily drives the urgent need for local recycling hubs, so nations aren't left entirely dependent on just a few isolated regions to power their entire transportation grids.
Because here's the thing, those geographic bottlenecks, they lead directly to massive price swings. Battery metals make up nearly 60% of the total cost of a battery. So when you see historical price spikes, like lithium jumping from $5 up to $20 a kilogram, or cobalt tripling to $90, that can completely derail a manufacturer's budget. For an investor, this makes an incredibly compelling case for risk mitigation. Setting up closed-loop, domestic material recovery isn't just an environmental win anymore. It's a strictly necessary financial hedge against global supply chain disruptions.
Which brings us to Section 2, transport risks and battery lifespans.
Before these heavy packs can even reach a facility to recover those valuable metals, we've got a logistical nightmare on our hands. You can't just toss these on the back of a standard flatbed. Moving them involves strict Category 9 hazardous material regulations. There are incredibly severe thermal runaway risks, which are essentially unstoppable self-heating battery fires if the packs get damaged. So if you're making a checklist for safe battery handling during transport, it is exhausting. You have to conduct rigorous international safety testing, fully discharge the energy, and use highly specialized packaging. Naturally, all these intense safety regulations make shipping over long distances insanely expensive. And that, once again, strongly incentivizes building local, regional infrastructure over international shipping.
Moving right along to Section 3, remanufacturing and repurposing. Before we even think about chemical recycling, we have to ask, how do we maximize a battery's value? Because tearing it down to base metals right away isn't always the smartest move. Here's a quick step-by-step on assessing a battery's state of health for value preservation. First, you run diagnostics. If the pack still delivers more than 80% of its original capacity, you go with remanufacturing. Maybe swap out a few degraded modules and drop it right back into a car. If it's below 80%, you repurpose it for second life applications. Think stationary energy storage for a solar grid. This extracts way more value beyond its original use. Only after exhausting these options do you move to step 3. The ultimate final stage of chemical recycling.
Okay, let's get into the nitty-gritty. Section 4, comparing battery recycling technologies.
When a battery finally hits the absolute end of the line and repurposing is off the table, the industry looks at 3 primary industrial pathways. We have the high-heat smelters of pyrometallurgy, the liquid chemical extraction known as hydrometallurgy, and the highly experimental frontier of direct recycling. Comparing these methods side by side reveals some stark differences, especially regarding industrial feasibility. Pyrometallurgy is super mature, heavily established in Europe and North America, and you literally don't even need to sort the batteries first. But the downside?
it completely misses recovering lithium and aluminum early on, losing them to slag. Hydrometallurgy, which is the primary choice in Asia, gives you high purity and recovers almost everything, but it requires intense, expensive pre-sorting. And then direct recycling? Well, it sounds amazing on paper, but currently has very low industrial feasibility, since it's mostly stuck at the lab or pilot scale.
And we really have to evaluate the environmental impact here. Pyrometallurgy acts like a massive blunt instrument, burning a ton of energy and pumping out direct CO2 emissions. Hydrometallurgy is more of a precision chemical extractor. It operates at much lower temperatures, which gives it a better carbon footprint, but it trades that for a complex, expensive wastewater management problem. Now, to be clear, both of these closed-loop methods are light years better than the massive carbon footprint of primary mining from the earth, but evaluating their life cycle energy consumption shows us they are still far from perfect.
So, this brings us to direct recycling. How does this actually differ from the other two? Well, while the pyrometallurgical and hydrometallurgical methods completely break the battery down into elemental liquids or base alloys, direct recycling acts as a structural preserver. It uniquely tries to harvest and regenerate the original crystal structure of the battery's cathode. Why is that such a big deal? Because maintaining that highly engineered crystal structure skips massive steps, saving an immense amount of energy and manufacturing costs compared to building brand new cathodes from scratch.
All right, Section 5, Technical Barriers and Feasibility.
Now, as much as these technologies are critical for long-term industrial sustainability, mass adoption is facing some seriously frustrating roadblocks. First off, there is virtually zero standardization. Batteries come in wildly different sizes, shapes, and they use heavy glues that make them an absolute nightmare to take apart. Plus, because you've got all these mixed cathode chemistries out in the wild, recycling plants have to invest in complex, expensive sorting tech. Combine all that with low collection rates, and these multi-million-dollar facilities really struggle to hit the economies of scale they need. We also have to forecast future market shifts, and this quote really highlights the problem. Traditional pyrometallurgy relies heavily on the high value of cobalt to make smelting profitable, but there's a massive shift underway. EV manufacturers are rapidly moving toward lithium iron phosphate, or LFP, batteries, which contain absolutely zero cobalt. This transition is severely threatening those existing traditional business models, basically forcing the industry to innovate faster toward hydrometallurgical or direct recycling solutions. Finally, Section 6, the future circular economy. So how exactly does the global market respond to these complex logistical nightmares? Just look at this map of current recycling hubs. It is incredibly sparse. Facilities are highly concentrated in just a few specific regions. When you combine that reality with the massive transportation costs and the thermal runaway risks we talked about earlier, it paints a very clear picture. Transporting hazardous spent batteries across the country, let alone the world, is just an impossible bottleneck. We desperately need a distributed, local network. This is exactly where government oversight steps in to force the issue. Domestic regulations and extended producer responsibility laws are practically demanding the creation of regional hubs. Take the European Union, for example. Their mandate requiring 50% recycling efficiency by 2030 is aggressively incentivizing capital investment into local, closed-loop infrastructure. These policies are the vital anchor we need to ensure the circular economy scales up in time to handle that incoming wave of spent batteries. Thanks for hanging out with me for this explainer. I want to leave you with this final thought. We know those 21 million battery packs are coming. We know the technical barriers, the rapid market shifts, and the immense financial value locked inside them. The real question is, will the industry and local governments actually innovate and scale these recycling methods fast enough to truly close the loop? Because if they don't, we aren't just missing out on a massive opportunity, we are literally just replacing our fossil fuel dependency with an entirely new, deeply complex supply chain crisis.